To know, do you have idea in computational or theoretical chemistry?
Assume I don't have
Okay,
any
don't
knowledge.
worry, I know how to communicate my work to
Okay.
everybody.
Excellent, thank you.
I'll definitely do justice to that. Okay, so basically, the goal of this research is how can we convert methane to methanol?
Oh,
So there are current processes where we produce methanol from. So, but the challenge is that, many people try to either from reduction of ethanol, either from reduction of ethane, oxidation process, where we produce that from. But our goal is to start from methane. Why methane? Because methane is a greenhouse gas, the climate change effect. So we want to see, can we convert this methane, which is a many-storage, to a useful product? And methanol is what we observe to be a stock product. The stock that is very useful. So, however, this process has been tried. If you look at this chart that we have here, the first chart here, this shows various processes that have been real attempts on converting methane to methanol. However, there is a challenge. Once we get this methanol, it's very difficult to isolate it. So further side reaction occurs and it results into unwanted product that we don't want. So we try to look at why is this taking place. So we observe that the CH bond in methane is stronger than the CH bond in methanol. That makes sense because oxygen is electronegative in methanol, so it makes the bond very weak. So as you catalyze the process, the CH bond, as you break the CH bond in methane, the automatically auto-oxidation is taking place. So the CH bond in methanol is breaking because it is less stable than the CH bond in methane. So that's a big problem, and we are trying to look at why this occurs. So we observe that the reason is electronegativity, the polarity of the system. Catalysts are made up of a metal, central metal, and the ligand. The ligand is the one pushing the electron to the metal center, while the metal center is cationic in nature. So we discovered that a metal center that is electron loving, once it sees oxygen that has electron rich, there will be a reaction that occurs, and this actually makes methanol, our product that we're looking for, to be less stable. Therefore, auto-oxidation, like it's an auto process, it happens on its own. Once you bring catalyst close to it, auto-oxidation takes place. So this chart explains what is happening. When you have a metal center, this is a metal center of a ligand. When you have those metal center and you're able to get this product, auto-oxidation takes place, it can give you any kind of product. These are just major ones that we are using as example here. But when we come here, we try to probe it. What if we force an electron upon a metal center? What if we have an ionic metal center? What will happen? So when we have an ionic metal center and we got our methanol in the process, we observe that it stopped. Why does it make sense? What does it actually make sense? We could see that there is a repulsion taking place because the metal is negatively charged. Oxygen is electronegative. There is no place it can disperse that power of its electron-rich prowess in the system. So we now have dispersion taking place in the system, then that auto-oxidation could not take place. So it makes it more stable at that point. This mechanism explains what is happening. This particular mechanism, we call it ping-pong mechanism. Why? Because we make a metal center to be electron-rich. So it gives electron into the system and it takes it back at the end of the day so that we can isolate our methanol. And this is it. This is an ionic metal center. What you have here is a CH bond. So any kind of CH bond, whether that of the methanol, which is that of the methanol. So when we bring an anionic metal center into the system, it changes the property. This is a fissile ball activation. This is where the activation is taking place. So at the end of the day, we no longer have C to H bond again. We now have C to metal to H bond. So, and that is why the splitting at this point takes place, because the carbon are no longer directly attached to themselves. They are now attached to themselves via the metal in their middle. So at this point, we discover that they are more stable. What you have here, this red ball is oxygen, is a molecular oxygen. We bring a molecular oxygen into this system to form an encounter complex. So this encounter complex is what we observe to be very stable because of the negatively charged impulse process that we use on of the metal center. So because the metal center is negatively charged, the encounter process is more stable than methane that we're starting from. And I will show you with all those charts, but we're getting there. So because of the repulsion between the anionic metal and the oxygen that is negatively charged, so it is very easy to isolate our product, which is the methanol that we're looking for, and the metal itself. So we can easily take the metal away from the product, which is why we are trying to study why this happens. A paper is published on this work, which is being negative can be very positive. It's in Royal Society of Chemistry journal. So that's the title of the paper. Now, let me go into the theoretical and experimental process that we did here. Experimentally, how can we achieve a metal center? An anionic metal center. That can be done through laser ablation. So when you bring a metal to laser, you vaporize it. So a photon is ejected from that metal. So it is very easy to impose electron on that system through direct electron capture. So that can be done to achieve experimentally. But we are doing this theoretically to confirm an experimental process, the result that we have from our experimentally. So this result, experiment is done in collaboration with Bowen's laboratory from Johns Hopkins University. So this is a collaborative work from an experimentalist and we are theoretical chemists. Now, this is a photoelectron spectra. What's a photoelectron spectra? It studies the binding energy of the system with the photoelectron intensity. So the binding energy of the system, we take the energy between the product and the reactant. That gives the binding energy of any system. So once you take the energy difference between the product and the reactant, that gives the binding energy. So we just convert it to electron volt, which is what we do in the system. Now, we tried this with 5 different metals: copper, silver, cobalt, gold, and iridium. So we observe for copper that when we study the spectra we got for the metal anion is this. We now correspond after introducing methane into the system. What's the difference? If you observe here, we have a reduction in the peak, which shows that an encounter complex is done here. How do we get this experimentally? We got this by running a DFT calculation. DFT is a density function theory, so it's an electron cloud being formed upon the system. That's what iteration is done computationally. So it will take the lowest energy until it gets to a lower energy, our calculation will converge. So at the lower energy, it is this lowest energy that we take and we compare it to experimental value. So when we run the calculation, we got a value around 1.3 or 1.4, which explains why this happens. And if you correspond this to the metal itself, this strong peak, you can see that there is a reduction in the peak. It has come down. So telling us that it is no longer the metal alone, something has happened at this point, which explains. So when we check this value, it corresponds to our encounter complex. That's why we're able to put this there. So we went further because we have other peaks. How do we see other peaks? We have to do some higher level of theory, the calculation. We do couple cluster calculation and multi-reference calculation. Why this couple cluster? If we have a lot of people in this room, right? So if we want to check how the condition is, assuming that the condition of everybody in the room are the same, because for a gas system, we keep them in a particular condition. We set a boundary for them. So we expect that the condition in that particular system is the same. So we can take the interaction between 2 of the gas molecules as a representation for others. That's what we do at couple cluster level. So we take 2 of it as a representation for others, but it's a single reference calculation. So we expect it to return for us a single energy that will be able to correspond to experimental data. So when we run further at the calculation at couple cluster level, we got a peak for our product. When methane reacts with the metal, it will give something very related to our methanol complex. So methanol is CH3OH, right? So what we currently have is CH3 with the metal in the middle and the H, so we can easily bring in our oxygen at this point. The major problem is at this point where we form this. If we can achieve this, we can bring in oxygen. So our goal is to form this and introduce the oxygen. And that is why we are trying to form a system that looks like this. So when we run calculation for this, at CCSDT level, couple cluster level is a single reference, so it came back with a single value, energy value. So when it came out with a single energy value, we corresponded with for all of these, and it makes sense. The value we had is very close to experimental value. We had something around 2.7. So what they had was around 2.81. So we have something around 2.78, which really makes sense and corresponds to this value. However, there are other peaks. How do we see other peaks? So we have to go to another higher level of theory. So what we did was we did multi-reference calculation. What does multi-reference do? Multi-reference study the dynamics of the system. I told you couple cluster is single reference, it is static, but multi-reference is dynamic. For example, copper is S2D9. What if the system resulted in X1D10? So these are degenerate systems. Their energies are the same, but not equal. So their energies are very close. So at CCSDT level, we cannot see that. But at MRCI, which is an advanced calculation, we were able to see that. In fact, we saw a lot of the possible arrangements of electrons in the empty orbitals. So which gave an explanation to three other peaks that we have very close to this, and we got them at MRCI level. So we replicated this process for cobalt and iridium. Now for cobalt is a very strange system. Why? Because it's S2G7. Cobalt is STG7. So we can have several degenerate orbitals. I mean, with that, and there could be possible spin switching. We have forbidden transition and unforbidden one. Because if we start with singlet, we want to end with singlet. But for cobalt, there is every tendency that there is forbidden spin change from singlet to triplet or other way around. So we try to study this and observe what actually is going on. Now, if you look at silver and gold, the peak for the metal itself and after the introduction of methane, they look pretty the same. It seems like there is no change. So why do we have this? So we have to look into, can we get the reaction coordinate? Let's check the energy profile of the system and see what actually happened. So when we did the energy profile of the system, this is the counter complex that we form with the blue peak. The red peak are the products that we have. Now, the counter complex we have at this point, the energy of this counter complex is more stable than the product. That does not make sense experimentally because you don't want to form a less stable product. That means you're not getting the product. So computationally, when we create an energy profile, we want a product to be more stable than the reactant. That shows we are making having a very good point. That's one point. Another point is that the transition state for both silver and gold for this particular system is pretty high. So which actually tells us that the energy barrier is high. It's very difficult for the system to cross to go and form the product. We were able to see this product being formed because we are running this theoretically. That was able to make this prediction. So the energy will be less stable. That means experimentally it won't cross this barrier. So that explains why we didn't have this peak. Now let's go to why we have multiple peaks in cobalt and that of iridium. However, I must state that for cobalt itself, the system worked perfectly well because it gave the peak that corresponds to this, theoretically, and we have explanation for all of these as stated in the system. So another thing we try to look at is why do we do cobalt oxide? Because we observe that cobalt oxide and the counter complex for cobalt oxide and that of the counter complex for cobalt and the methane, they have the same molecular mass. So we have to run the spectra and we observe that the spectra are different. So we are so sure we are working with this process. Now, cobalt gave the lowest energy barrier, so which gives us a very good idea. And at the same time, it forms a very low product as well. So which shows that the counter complex we are having at those points is more stable than the methane when it started. So once we're able to have that, it gives us insights into the next thing to be able to do. The same happens for copper and that of cobalt. But for iridium, when we run that of iridium, we have the challenge with iridium. Our experimentalists couldn't get the spectra for iridium containing hydrogen. They had to use the isotope of hydrogen, which is deuterium, before they could get this. And when we run our calculation, what we're doing is we are transferring the hydrogen one by one from the methane. So when we transfer the hydrogen, the first hydrogen to form this complex which is our goal in this research, and we transfer this hydrogen, it gives this. And when we transfer a second hydrogen for others, it is giving us the same structure as this and the same energy as this. So which shows that we have gotten to the most stable product. But when we did for iridium, it actually underwent transfer until there is a complete transfer from hydrogen to iridium, from carbon to iridium, which is why our experimentalists do not work with hydrogen, they work with deuterium. So, and if you look at those peaks, there were agreements, but they are not that close compared to others. If you look at the peak where we pointed them, they were not close to where the peak actually existed. Why? Because they work with deuterium and we worked with hydrogen.
So your best model right now is with iridium.
Yeah, the best model now is because there is a complete transfer of hydrogen to this particular system. So we've gotten our breakthrough by forming this encounter complex, this particular complex. Then the next thing is for us to introduce oxygen into the system. But the goal and the challenge that has been over time is getting to those points where the complex, those HMCH3 will be more stable than that of the methane itself, which we've been able to achieve. So the next line of action for us is to introduce oxygen into this system and see if we're able to produce methanol, which we are so certain we're able to produce because we've tried this based on this particular work. So that's the goal of this work. We are able to adopt methane to produce methanol directly. But currently what people do is they try from either method reduction, oxidation from maybe methanol or acetone or formaldehyde, something of that nature to produce methane. But we are starting directly from methane to produce methanol. And we are making significant progress. So